All right. Good morning, everyone. Morning, everyone. So, quickly, let me turn the screen on here. I wanted to talk a little bit about Monday's discussion about. We're talking about motors. What end of the motor is the north side or the south side of either the stator or the rotor of the motor? Okay. So I think the first part of this discussion is it's confusing. The second part is it doesn't actually matter all that much, because what we really need to know is what direction the flux is flowing. That's the primary thing we're going to look at. We're trying to understand in terms of convention of north and south in the motor. And then we'll go through some examples in the book and kind of talk about that really quick. So I just want to show some elements of the book that you've been using and kind of talk about it in that sense. So where's this figure I wanted to show? Okay, so two things to consider here. I think if anyone were to see this little quick electromagnet, right, they would see that we have current running this direction. Via the right-hand rule, we have flux in this direction. And so just like your homework problem from the previous week, we would say that this is north and this is south, right? So we have flux going outside in this direction, right? That would be the convention we're kind of really comfortable with, right? Now the difficulty comes in that if you look at the case on the inside, just to take a step back, we said that the flux runs from north to south always, right? That would be the way in which we look at this for flux that's going on the outside of this electromagnet, right? But now there's also flux going on the inside of this electromagnet as well. And so that has a direction. And so that gets confusing now when you start to talk about, say, the stator location, which is the stator is this big box on the outside here. And in the book and other books, etc., it denotes this side as north and this side as south, right? And so if we were to map this electromagnet to this, we would say, okay, each of these stator elements has a north and a south associated with it. Right? Just like this one has current running exactly the same way, and this has a north and a south associated with it. Okay, so you can see how it's starting to get a little bit more complicated here. So the most important thing to keep in mind, though, is that the flux in this magnetic circuit is going from, okay, if we look at what's happening from this electromagnet, we have flux going in this direction. It's consistent that we have flux going in this direction here. Right? And so if I look at my flux loops, I have flux now going through my rotor, because my rotor is primarily composed of a ferrous structure, and then it's then traveling to complete the circuit through the frame of the stator. Okay, so now we have to talk about the north and south for the purposes of what is working on the rotor. And so for what is working on the rotor, flux is going in this direction, so this is the north side, and this is the south side, because flux is going from north to south. Okay. Now, if we were to say, okay, here's one individual electromagnet unit, I would say that this is the north side, this is the south side of this little element, and this is the north side, this is the south side of the element, but it gets more complicated when this is in kind of an assembly. So my main message here, what side we call north, what side we call south, really not that important. The most important thing is to know what direction the flux is running in your system. All right. Any questions on that idea? The labels are confusing, I agree. There's not really a good system for it, but what we care about more is what direction the torque is in. Okay. All right, now that we're all confused and we don't know what direction it's going to be, we can start talking about motors more. All right. So this, Okay, I'll save these notes and then put them up in Carmen so you can take a look at these as well. Connects. Okay. Let's see what's going on. That's probably it. Okay. Try it again. Okay, so here's where we ended on Monday's class. This is in the same convention that we just talked about. Inside the stator here, we have flux running from north to south, right? So in the location of where the rotor will be in this, say, central region here, given by green. This is rotor, right? Flux goes from north to south. That's what we're working on there. So the next few little, I guess, comments here is going to be leveraging both the notes here and a video. Okay, so the video, I think, explains the action of this motor better than I could possibly do because it's nice and animated, but we're going to be going through this in a few different steps here. So the video, let me pull this up. The video is just purely pulled from YouTube, so it's nothing, fancy or something that you couldn't find on your own. But I think it nicely illustrates some of the actions of really basic motors, including the really basic motors I have on my desk here. All right. Play back. Okay, so then why is audio not working? Volume. Okay, there should be audio here. So let's do something here. Let's see. I wonder if it's just because I'm using my laptop and not the Podium PC.
There's no such thing as a perfect writer. This is why I always graduate to check my copy.
Okay.
You can find DC motors in many portable home appliances, automobiles, and types of industrial equipment. In this video, we will logically understand the operation and construction of a commercial DC motor. Let's first start with the simplest DC motor possible. It looks like this.
Okay, so to note, so they're not showing the electromagnet on the outside of this. They're just showing the salient poles. Remember the definition from Monday? This pole here from the stator would either be made of a permanent magnet or it would be made of an electromagnet, which is a coil running around this with a current through it, and then the flux through the stator is directed from north to south in here. So it's not showing the coil, it's just showing the direction of flux.
The stator provides a constant magnetic field, and the armature, which is the rotating part, is a simple coil. The armature is connected to a DC power source through a pair of commutator rings.
So I'm going to pause there for a second. And so with this discussion in mind, I'm going to pass around both of these motors in case you were not able to see this on Monday. Some of the elements that you see here, so try and map what you see here to this video and also our discussions. Some of the elements that you'll see, you can see it in both these pretty well. These commutator rings, which is where my cursor is right here, or commutators. These are also sometimes called brushes in what you call a brushed DC motor. These are these elements right here. These are these green things on this motor, and then they're copper colored on this one. Okay, so these brushes are in decent shape. These ones are all torn to shreds. And so we'll see, you can take a look at this. Oftentimes the motors fail because the brushes wear out, so you can see an example of brushes that are really torn apart on this one from overuse of the motor. So I'll pass both these around. This is a magnetic coil which creates the flux in the stator. This has a permanent magnet which causes the flux. That's these heavy pieces here on the outside. That's a permanent magnet.
When the current flows through the coil, an electromagnetic force is induced on it according to the Lorentz law, so the coil will start to rotate.
Okay, so I'm going to pause right there, and then we're going to draw some notes on what's going on right here. So if we were to then map what's going on in the video to this discussion, we would see the following system right here. What we would see okay, so we have stator with a north pole and a south pole. So that means we have a flux of the stator which we can give as BS, S standing for stator, going in this direction. And then the configuration, I'll switch back to the video in a second, but the configuration of the video for that second was that we have then the rotor is in this orientation. Okay, and we have, just in the configuration used in the video, we have current going into the page on this side, and we have current going out of the page on this side in the rotor. So we can talk about what's the north side and south side of this, of the rotor in the middle, but it doesn't really matter all that much. What we really care about is in what direction is the force on the two different legs of this rotor, and therefore what direction is the torque on the system. Okay, so to talk about that, we would say that so this is flux given by my fingers in this direction. And then I have current into the page on the left side, right? That's my thumb, so that means then the force is down on the left side of the rotor. If I look at the case on the right side, I have flux in the same direction. I have current coming out of the page that's coming at U. That means we have force on this direction. So that means I have some sort of force in this direction on the elements of the coil or on the left-hand side of the rotor, and I have force in this direction here. Right? Okay, so combined, right, I'm going to have a torque that's going in this direction. So at this current point in time, there's a torque that has a torque and it's in the counterclockwise direction. Right? Okay. Any questions on that? All right, so we'll play the video for just a little longer. Okay. So you can see this is more of a 3D or isometric view of what's going on. So same idea, current into the page on the left, into the board on the screen on the left-hand side, out of the screen on the right-hand side, forces in this direction on these rotor coils.
You will notice that as the coil rotates, the commutator rings.
Okay. So because of the torque, right, and it's on some sort of bearings, it's going to cause it to rotate until we get to this location. So this location, just to note, we'll talk about the forces in a second, but at this location, we've rotated 90 degrees. Now the force hasn't changed direction, right? So now if we start to look at moment arms, we're going to see that the torque is going to start to disappear. So going back and just kind of illustrating this, same idea, the stator doesn't change in a DC motor. So everything with the stator stays consistent. All right, but my rotor has rotated 90 degrees. And for this point in time, our current is going in exactly the same direction. Okay? So the force is going in exactly the same direction. Right. So then the question is, what is the torque on this configuration right now? 0, right? It's 0 because the moment arm went to 0, right? Because at this point in time, basically the force is just pulling out. It's not actually exerting a torque on the rotor anymore, right? So if all motors were just as simple, they wouldn't work, right? So we need to engineers come up with solutions to solve this issue. Okay. I'll watch a little more.
Connect with the power source of opposite polarity. As a result, on the left side of the coil, the electricity will always flow away, and on the right side.
So I'm just going to reverse. I'm going to reverse for a second here. There you go. Let's start here again.
When the current flows through the coil, an electromagnetic force is induced on it according to the Lorentz law, so the coil will start to rotate. You will notice that as the coil rotates, the commutator rings connect with the power source of opposite polarity.
Okay. So just to comment on this statement, so this is probably the best scene in the motor that's sitting over there right now. Okay. So if you take a look at where you can see that the commutators of brushes are contacting this commutator ring. That ring is split into, I don't know how many, there are probably somewhere around 20 different channels, right, or electrical contacts. As the motor rotates, it's switching between which of these coils in the rotor are actually having current running through them. Okay, so the majority of them have no current running through them at all. It's just the ones touching the commutator rings or the commutator at that point in time. This example here is just when you have just a single pole. So you only have two splits. And this is, we'll talk about this in a second, this would create a very jerky motion. The more of these splits you have, or the more coils you have, the smoother the motion you have. So the video will talk about that in a second. But so since we've made this transition, so just to reverse just a second here, okay?
The commutator rings connect with the power source of opposite polarity. As a result, on the left side of the
Okay, so what has happened after we've, these stationary brushes have now switched, and now the current is going in the opposite direction. And so the new schematic that we're going to have is this one. So we have the situation, again, stator doesn't change. north, south, BS. Okay, so now that we've crossed over 90 degrees in terms of rotation, we have flipped the direction of current. So this bottom image is just a few degrees, maybe 10 degrees, 15 degrees more rotated than this image here. But the current has changed direction, and so therefore current is coming out of the page at the bottom and going into the page at the top. Okay, so same analysis as before. Okay, so B field in this direction. Now current is going out of the page at the bottom. That's my thumb coming at you. Force up. Right? Top one. All right. B field this direction. Current going into the page. Force down. Okay, so then our torque is in the same direction. Let me label these consistently here. Torque. And then here's a case of torque is equal to 0 in this scenario. Yes?
What does this all mean?
Our first one. I find it hard to believe that no one got to that. How many were we? Fourth, fifth week? Okay. So what does this all mean? So this one's easy. This one is basically how DC brushed motors work. This is the main functioning behind this, right? In terms of what are the internal guts of a DC brushed motor. So in terms of what this means to you as an engineer, DC brushed motors are really, for the most part, these are the least expensive of motors. They're everywhere, and they're everywhere, especially when we talk about servo-controlled systems. So we'll talk about servo-controlled systems in this class quite a bit, which is how do we do a lot of positioning type tasks or velocity control tasks. So we'll get into AC motors in a little bit. Those are in industry as well, everywhere. That's what you want, really consistent speeds. But this is kind of fundamentals of the most basic motors that you see in industry. If you're an engineer long enough, you will inevitably, if you haven't done so already in your internships, et cetera, had to buy a motor or use a motor. If you're in engineering long enough, you will have to use a motor, buy a motor, spec out a motor. It's going to happen, right? So it's good to know kind of the basics of how the things work, right? All right. Yeah, no skipping through that section of your notes. All right. Okay, so just some notes. The long name for this type of motor is called a brushed DC motor. They come in a variety of different forms. We'll talk about the parallel or series DC motor, or sorry, parallel or shunt DC motor. We'll talk about the series motor. We'll talk about a permanent magnet version of the motor. So the one that's right in the middle, like I said, is the permanent magnet one. The one that's farther back a little bit, that's either series or parallel. We'd have to look actually at how it's wired up. It's really tough to tell unless you look at the path of the wiring. And so we'll talk about those, but I mean, these are all in the realm or what they're called DC brushed motors. So the brushes are the spring-loaded contacts. Those fail in motors quite often. As you can imagine, this thing is spinning, so the brushes have to be in contact with the commutator, right? And if you say run this for hours and hours and hours, those brushes are eventually going to wear out because of friction wearing them down, right? And so brushes are a common thing that fails on these type of motors. I'll play the rest of the video because I think it's illustrative of the next thing I'm going to talk about in terms of how do you deal with this torque issue. So right at this transition, the torque goes to 0, which you can imagine is a bad thing, right, in terms of having consistent performance.
This ensures that the torque action is also in the same direction throughout the motion, so the coil will continue rotating. But if you observe the torque action on the coil closely, you will notice that when the coil is nearly perpendicular to the magnetic flux, the torque action nears 0. As a result, there will be irregular motion of the rotor. If you you run such a DC motor.
Okay. So switching back to that kind of discussion, if we were looking at just a, yes?
On your notes, you draw like the B field of the rotor too.
Yeah.
Does that just not, is that like this small enough that it just doesn't affect like the force?
So the B field is coming from this rotor. And I think the main thing to state is that it's not going to be all that important, I guess, to be. So what we really care about this discussion in terms of, you have a current running through a magnetic field. What direction is the force on that coil on that certain side, and what direction is the torque? Okay. So you're definitely going to have these interacting B fields, but they are going to be, for one, they're going to be, I guess the best way to say it is, it's going to create, the main thing, I don't know, anything I talk about just probably confuse the situation more. Look at the magnetic flux from the stator, and look at the direction of current from the rotor. That's my best advice to you. Okay. So going back to the video here, so what the video is explaining is that if we just have a single coil in the stator that has then two contact points, we would have torque that's always in the same direction, more or less. This is the angle of rotation of the motor, and then we'd have 180 degrees or pi, 360 degrees or 2 pi, and then in between. Okay, so going from the orientation that we started with throughout this whole discussion, when the rotor is in this orientation, this very top orientation, that's where we're going to get the maximum torque. All right, that's because our moment arm between the force and the center of this rotor is the largest. Right? As I rotate, this moment arm decreases, and it eventually goes down to 0. So if I look at what's going on with the torque, it's going to follow approximately a sinusoidal pattern here, or cosine pattern. So where it gets to 0 at pi over 2 or 90 degrees rotation, we're going to have then commutation or switching of the current. So it's going to go back up to pi and then down again. And if you can imagine, as the video showed, it showed this really choppy behavior. So you can imagine if you had a motor that was so simple like this, it'd be extremely choppy in terms of your torque you'd get. Right? So it'd be really weak at 90 degrees rotation. It would be strong at 0 or pi or 2 pi angle of rotation, right? So engineers have pretty smart people. We've figured out ways to get around this. So here's the choppy motion showing.
Trick to overcoming this problem. Add one more loop to the rotor with a separate commutator pair for it. In this arrangement, when the first loop is in the vertical position, the second loop will be connected to the power source. So a motive force is always present in the system.
So this is the case of 4 contact points.
Moreover, the more such loops, the smoother will be the motor rotation.
Okay. So this looks a lot more like what's being passed around the room, right? A lot of different coils here.
In a practical motor, the armature loops are fitted inside slots of highly permeable steel layers. This will enhance magnetic flux interaction.
Yeah. So you can see that much better in the permanent magnet motor that's being passed around. The one that has electromagnet to drive it is a little bit more difficult to see.
Spring-loaded commutator brushes help to maintain contact with the power source. A permanent magnet stator pole is used only for very small DC motors. Most often, an electromagnet is used. The field coil of the electromagnet is powered from the same DC source. The field coils can be connected to the rotor windings in 2 different ways.
Okay.
Parallel or series.
Okay. So that's it for the video. We'll talk about the parallel versus series distinction in a second, what that means from an electrical point of view. I just wanted to revisit the idea of this torque ripple. So this chart I have drawn right now is an example of a really bad torque ripple that you get if you only have 2 contact points. You can't buy a motor like this. No one would sell it. They'd be out of business. So what you have is the cases where you have a lot more of these contact points. Okay, so you have some sort of Tmax you get out of the system, and then the actual torque profile is a ripple, okay, as you switch between the different loops of the rotor. So the reason why the reason why I mentioned this ripple is quite important. So for the purposes of modeling motors in this class, we're not going to really model this commutation, right? We're going to say this ripple is so small. But if you work in any type of robotics, motion control, etc., this torque ripple actually becomes quite important. This is really a disturbance to your system. So if you have a control system and you say you model it, you're going to probably model to the mean of this torque in terms of the current torque relationship. But at some angles of rotation, you're going to get a little less than that. Some angles of rotation, you're going to get a little more than that. And that creates some inconsistencies in your motion, which will definitely reveal itself. And if you're looking at really high precision robotics, this becomes an issue. That's not really a topic for this class. That's more of an advanced topic. But I think everyone who's going to be an engineer and use motors should realize that with DC motors, you're going to get some sort of ripple behavior from it. Okay, so going back to this discussion here, oops, for some reason this page isn't blanked out. None of these are, okay. Okay, so I did not get as far into this as I thought I was going to. Let me, I think I'm writing clear ones. Nope. So I'm doing it wrong. Oh, there we go. Okay. So let's talk a little bit about the type of torque you would get on the system. So going back to our discussion that we had before. Okay, so our simplified drawing for a motor, north, south. All right, so current into the page on the left-hand side, out of the page on the right-hand side, and we said we had this force. And this force. All right, and then we'd have some sort of dimension, which is the distance between the, say if we just have one coil, or we can say the center of a bundle of coils, distance r. This is going to be a dimension of how basically wide the radius is of your rotor. Right. So if we want to look at considering the force on a single coil segment, all right, so this would be the Bly law, right? So this is going back from the very early discussions of E&M, or so I guess the later ones, we're looking at this is exactly the same as what we discussed when we talked about moving coil transducers. Okay. So the Bly law was BLI sine theta. Now theta here is, I'm just taking this directly from the equations that we talked about before. Theta is not the angle of rotation here. So sorry to mix things up here, but this theta here is the angle between the B field and the current. Right? So we have the B field, field draw here, we have the B field in this direction, and then in the case of the left-hand side, the current is going into the board, and so my thumb and my fingers are at 90 degrees from each other. Right? So we're actually going to get the maximum amount of force in this orientation. So engineers know physics pretty well. They make sure that the current is running perpendicular to the magnetic field for the most part, because that's when you're going to get the most amount of force out of the system. Right? That's when you get the highest energy transfer. So in this case, for all motors you'll see, really, unless there's some special cases I'm not really too aware of, this is going to be, that decides to show up twice now. Great. Okay, Control Z does not appear to work. There it goes, okay. Okay, you'll have to live with that. Again, L is length into the page. Okay, so this we really can't see, but this is the length of a coil segment in the page direction. All right, so this is going to simplify into, for a single coil, to BLI, because we have sine 90 degrees. But we're going to have, so this is the force on one side of this, right? What we're going to have actually is, if we look at the torque in this exact configuration, torque is going to be equal to two times N, if we have N coils, times R. And we'll get into the case when this is not perpendicular to the B field in a second. BLI for the torque generated in this configuration. All right, so if we have a slightly different configuration, so we have a rotation of gamma, here. We're still going to have the same exact force relationship in terms of the force on this coil is exactly the same, but now my moment arm has decreased. So this is now going to be torque is going to be equal to 2nr BLI cosine gamma. All right. So this entire term out front has a name that's often used, and you'll see this on a lot of spec sheets. And this is oftentimes given by K tau, or what's called the torque constant. All right, and it's in units of Newton meters per amp. Okay, so what the torque constant gives us is basically the relationship for a given motor, it gives us a relationship between current put into the rotor versus torque produced by that rotor, right? So if you look at spec sheets, you'll see exactly on there a torque constant. Yes?
So, two questions. So, like, torque, normally it's a force and a lever arms. Why are we including the number of coils?
So the number of coils determines how much force you get, right? So the first equation here is the force on a single wire, right? And now we're going to loop n wires around. So if you take a look at the motor that's right around the room, right, you don't see just one wire making one of the loops, right? You see a bundle of them. Okay, so one gives you 1 unit of force, two gives you 2 units of force, and then all that.
And then is the L included in the number of coils?
Sorry?
Is L included?
Yeah, I'll write this out in a second for more concept so you can see it more clearly. But usually when you buy a motor, they'll provide you the torque constant. They're not going to provide you all these other dimensions which are, those don't change. Those are kind of baked in. So they'll give you the torque constant. Okay, so then this cosine alpha, because of commutation, this cosine alpha is somewhere usually around 1, because as soon as alpha gets a little bit large, it switches now what coil is activated, and therefore you're in a stronger torque position, right? So we're often going to simplify cosine alpha to be equal to 1, and so our relationship is going to be usually, so I'm simplifying this a little bit because this torque constant includes, back. I'm simplifying this a little bit, but usually the torque constant, if it's a permanent magnet motor, it's going to be just the torque constant provided. And if it's some sort of motor that has an actually electromagnet driven system, it'll also be given by the flux. Okay. So just talk about that for a second. I'm going to pull up a spec sheet here that I think will maybe help illustrate this. Okay, so in the afternoon recitation, the TA is going to go through and show show a DC brush motor, and you guys are going to run it, and you're going to look at also some other things that happen with the DC brush motor. I just want to show a spec sheet on this, just so you have an idea of what type of information may be provided. So the one that she's going to give you is one of these micro motors. All right. And if I look at the data sheet on this, we're going to see a lot of information, and I want to highlight just a few things here. Okay, so this is what I want to highlight. So item 11 here is in the torque constant, right? So that's precisely what we were just talking about. I believe this is a permanent magnet DC motor, so this would be pretty much then the relationship of the amount of torque you would get out of this motor for a unit of current, right? So if you look at what's given here, it's given you 0.32, and this is millinewton meters per amp, right? So this is really just a fraction of a newton meter that you get per amp. This is a pretty weak motor for this example I'm showing you here, right? So this would be a very common thing you would see in a spec sheet. Basically gives you an idea how strong this motor is, right, for a unit of current that goes through it. All right, like I said, this one's weak. You can see some motors, some of the bigger ones, get on the order of around 1 newton meters per amp. for something that you could actually carry around. And then, of course, industrial motors, they'd have to have like a hoist to lift. Then you're talking about many, many Newton meters per amp for the system, and also the ability to put a lot of current into the system as well, really high current into those motors. Okay, so that was a discussion of current. We should talk about back EMF as well. This is the fundamental mechanism that slows down motors. So back EMF. Okay, we'll look at this configuration here for a second. It doesn't really matter what direction the current is running in this for this scenario. So this is the case of alpha equals 90 degrees. Okay, so going back to our discussions of back EMF, we said that back EMF, which is the voltage caused in a loop of coil for something that's moving, is given by d phi by n times d phi dt. So that's n is the number of coils. Phi is equal to b times a. And A is the area that's interfacing with this B field, right? So we have rotor in this orientation, B field going through the rotor. This has a certain cross-sectional area that we have to consider. So A is equal to 2RL sine alpha. Okay, so when alpha is 90 degrees, the area is the largest. As alpha goes to 0 or 180 degrees, this area of intersection goes to 0 as well, right? Because the B field is not going through the coil anymore. And so oftentimes we'll see in terms of area, we'll oftentimes simplify this, saying that commutation causes this. Number to be given some sort of small angle approximation to be just be 2R L gamma, and we're going to have then a back EMF constant of 2NR BL, and then omega m. Right, which is d phi dt. All right, so oftentimes you'll see this expressed as a back EMF constant, oftentimes given by Ka, the flux, and then the frequency, or the angular velocity. Yes?
Why don't we switch to gamma with small angle approximation?
Sorry, this should have been alpha to make it consistent with what was before up top. Oh, sorry, this should have been gamma the whole time. Yeah. Sorry, it should never have been alpha to begin with. Yes?
And then when you have the tau equals AT by I, is it B?
IA, yeah.
IA.
It's just the armature current. Yeah.
Okay.
Yeah. So basically how much current is running through the coil.
On the outside.
Yeah, so that would be, so we have current, so this is current coming out of the board. It'd just be the magnitude of that current.
It'd be that current that's going
Through the rotor, yeah. Carson?
Is that different?
Oh, okay, go ahead.
Sorry, is that different than the torque for the BLI?
So this is, so all these equations here are all interrelated. So I was just starting with kind of the longest form of this, right? This is the force on it. The Bly law gives you the force on an individual segment of coil, right? And now we have n of these, so we have to multiply by n. And then we have a moment arm, which then allows us to talk about this in terms of torque. Right, so when we talk about rotating machines, we're going to care more about torque than we are force.
So, is phi then equal to cosine of gamma?
Sorry?
Well, we go from
cosine gamma. No, so the cosine gamma is usually, gamma is usually around 1. Or sorry, gamma is usually around 0. That's the maximum torque configuration. So cosine gamma is going to be typically around a value of 1 then, because of commutation. So we're continually switching what coil is activated. So when we're looking at this, most of the time we're looking at a situation where it's in this configuration at the top here. Right? By the time it rotates appreciably far from that, it switches which coil is active. What is the phi? Oh, so phi is flux. So we had B times B, which is your magnetic flux density, times your area, gives you then the flux. So these are just simplified relationships. I think the most important things in terms of solving problems in this class is going to be this expression, right? So torque is torque constant times the flux times IA. And then this expression in terms of the back EMF is the back EMF constant times phi times the speed of the motor. Yes?
Like your KT, does that not, it doesn't include the I, correct? For the torque, it's 2nRBL.
Yeah, so it's a little bit more complicated than that. So, so where's my cursor here? So we have, okay, so it really depends on the type of motor we're using. Maybe I should have split this out into different types of motors. So if we have an example of a permanent magnet motor, this B field is not generated by the current running through the system. Okay, it's a flux that is coming purely just from the system itself. It's some sort of, basically it's a flux that's coming because you have a permanent magnet, and that's going to be constant. So when we look at a permanent magnet motor, it's going to bake in that torque constant into this. If we have something that's activated by an external flux from an electromagnet, the torque constant is actually going to be completely different units. So I can't really give a straight answer to you because it depends on the type of motor we're talking about.
For this problem,
Use the bottom one, that this torque constant, basically torque is equal to torque constant times the flux times IA. All right, and we'll make it clear in the problems that we give. Yes?
We also be given the flux through the motor on the data sheet then, or?
I think an example I won't get through today, but on Friday we'll show you an example. So on the case of, say, the first motor that went around, flux is created by electromagnet. That is going to be dependent on the input to our system, because the more current I push to the system, the stronger that flux is going to be. The second one with the permanent magnet, we're going to assume that the flux is constant, right? Because it's coming from some sort of constant flux source. So it's going to depend on the problem. And I hope when we get through some examples of like series and shunt motors, that'll become clear that we'll always have to compute what the flux is for those cases. Okay. All right. So torque constant back EMF constant, important elements to consider here. Let's take a look at going back to the spec sheets again. Right. So I said item 11 was a torque constant, right? So that's in terms of units of basically Newton meters per amp. This here is then the back EMF constant. They're calling it KE. The book calls it KA. What this is giving is the amount of volts basically created by the system, right? So you have a motor. It acts like a generator as well. It creates a voltage across the armature or the armature or rotor coils. And then they're giving this in RPMs, in units of RPMs, right? So that's not going to be the most convenient for us often. Oftentimes we're looking at, say, radians per second. But it's basically the relationship between the amount of voltage created by that coil and the speed at which the coil or the rotor is rotating. Right. And you'll see pretty much any motor spec sheet, you'll see this information in here. Oh, we're out of time. Okay. Okay, we'll start talking about circuits diagrams for motors on Friday's class.